Okay, we're going to go ahead and get started here. Thank you so much for coming out on this March 20th. It's a little bit breezy today. Hopefully that's not going to affect our demos too much. We are from Emory University, and we represent several different organizations. Whoa! Don't stand there. Okay. We are from ChEmory, which is the Chemistry at Emory Undergraduate Club. We are also representing PAX, which is Pi Alpha Chemistry, which is our graduate organization. And we are also representing NEMACHE, which is our national organization for the professional advancement of black chemists and chemical engineers. So we have a lot of people who are working with you today. And so we have several demos to show you because science rocks and it's just so much fun. And we're so glad you could be here. So we're going to start with a demo called the CO2 Rainbow. And so we've got a couple of our volunteers for you, and they have a very tall cylinder of dihydrogen monoxide. You probably know that as water. But dihydrogen monoxide, it's actually a really interesting compound. A lot of different properties that are why we're alive. But we're going to add to that a little bit of something called Fisher Universal Indicator. Now, what we're looking at here is that different compounds can be more like acids, things like lemon juice, or bases, things like soaps. And this particular compound changes color depending upon whether you have an acid or a base. So we have a bunch of different colors. We can go from red all the way up to purple. And the more towards purple you are, the more basic it is, the more like soap it is. So tap water, and it's kind of green, which is actually neutral, pH 7. Which is very close to what your body needs. Your body runs at pH 2.35, no, pH 7.35 to 7.45. Oh, that would be a problem. All right, now to this, we're going to add some sodium phosphate tribasic. Ooh, what is that? That's just a base. And actually, that is the chemical compound of phosphoric acid that is in 7-Up and Coca-Cola. That gives it a little bit of a tang to it. So essentially, we're making flat 7-Up here. Okay? Now, what happens when we add that? Well, it's a base. So hopefully you can see that when we did that, the color changed. It turns towards a purple. Okay? So what we want to demonstrate to you now, though, is what happens with carbon dioxide. All right, now carbon dioxide, everybody's breathing. You're all breathing in your cars, and you're producing some carbon dioxide. And we've got carbon dioxide here. When it's really cold, it's dry ice. All right? It is 79 degrees below zero, and that's solid form. And we're going to add it here. Now, carbon dioxide is just made up of two elements, carbon and oxygen. All right? So let's go ahead and put it in there and see what happens. Now, it will turn to a gas, so we start to see some bubbling here. All right? Ooh, bubbling science, always a good way to start. But carbon dioxide is interesting. It doesn't have any hydrogens on it, but it is actually still an acid. And you can see, hopefully, we've gone, we're still kind of purple. What do we got now? Oh, we got to green. So we've gone from purple to green. And we got green here. All right. So as we go through, this is kind of odd doing demo shows like this, because normally we get to hear the audience go, ooh, ah, oh, and you are welcome to do that in your car. Maybe honk and tell us you like it. I don't know. But we're to green, light green going towards yellow. So that means, there we go, that means that this is an acid. And in fact, when we talk about carbon dioxide in the atmosphere and the acidification of rivers and things like that, this is why. Because as you get more carbon dioxide dissolved, the water becomes more and more acidic. This is actually why many of our old buildings are dissolving and things like that, because of acid rain. So the acid rain actually comes from this carbon dioxide. All right? So we've gotten down to what pH do we have here about?
5, 6.
About pH 5, 6 down there. The very worst acid rain or acid event that has ever been recorded was in Los Angeles, and they had something called acid smog. Now, acid smog, just like acid rain, but it sticks around. London used to have this a lot because they burn coal. And it had a pH of 2, which means it was very close to stomach acid in the air. It was not a good time to be in LA. All right, so that's our first demo for you, the carbon dioxide rainbow. So let's go ahead and switch on over here. We're just going to kind of keep on moving. If you have questions about the science, You are more than welcome to email me, and you can get my contact information to the Science Festival, or I'm actually just on the ChEmory Chemistry webpage. I forgot to introduce myself. I'm Dr. Mulford. There we go, Professor Mulford, Dr. Mulford, hey you know, whatever works. Okay, so the next thing we're going to do is we want to think about other things that chemists look at. So there was some of the ways that reactions can occur. Now we want to look at what are some of the effects that changing temperature can have on different objects. And so we're going to bring up all our materials here. Okay, we're looking for a racquetball.
I'm taking my cousin's birthday.
Nope, here we go. Oh. We like to have fun with our chemistry, and here, racquetball here. Wow, it is windy out here.
Yes. Hello, I am Courtney. I'm Landy.
Y'all want to see the rest of the show?
All right, so what we have here in this bucket is liquid nitrogen. So the atmosphere, what we are breathing, the air around us, has 78% nitrogen. It has 21% oxygen, and the remaining 1% is a mix of other gases. So at liquid state, what's here in this bucket, this nitrogen is negative 320 degrees Fahrenheit. That's very, very cold. You can't see it, but inside this liquid nitrogen is kind of a colorless liquid, and it has a very low viscosity, meaning that it's very fluid. So like water has very low viscosity, and like something like honey or oil is going to have much higher viscosity. So what we are going to do first is place in this racquetball.
How are you cooking somebody breakfast? How are you fixing somebody breakfast?
All right. Hello. Okay. And we are also going to place in this banana.
Can you see the show?
So, yes, a banana, like when you eat. So, because these are kind of, you know, thicker materials, they take a little bit of time to freeze completely. So we are also going to put in a balloon. Landy, would you mind blowing up this balloon? All right. Now, something like a flower that has a lot of water in it doesn't take a lot of time to freeze. So I'm just going to stick in this flower for a couple of seconds until it freezes. And are you ready?
Yes.
It shattered. Thank you. All right. So we're waiting for Landy to blow that up. What do you guys think will happen? Just think to yourselves. What do you think will happen if I were just to leave this bucket of liquid nitrogen out? So this is really, really cold. So if I were to leave it out at room temperature, what do you think would happen? The liquid would eventually become a gas. It all disappear into the atmosphere and become something that we breathe. Okay, so Landy, would you mind sticking that in? Or I can do it if you, with the safety gloves. All right.
You see the show? See the balloon?
Let's see. Can I give you this? Sure.
Just gonna use the tongs here.
See if everything has had enough time to freeze completely. Alrighty, I think we are ready. So now,
Banana is frozen.
I'm going to use this banana to nail in a nail into this piece of wood as a hammer. So a banana is usually pretty soft and mushy, right? The nitrogen made it so cold so that I can use it as a hammer.
Look, Langston, look at it, her nailing with a banana. Look.
And there we are. All right. I think we're ready to take out the ball.
She put it in
All right. Are you ready for this one? 3, 2, 1. Yeah.
Put it in the liquid and everything froze.
All right. I think now we are ready to take out the balloon.
See the balloon, Langston? Look, she put a balloon in there. She's ready to take it out. Oh, look at the balloon, Langston.
All right, let's see what the balloon looks like. Ooh, it's a poodle.
See that, Langston?
Some magic happened with that liquid nitrogen. It turned it into a poodle.
Put everything
Okay.
liquid nitrogen.
All right, thank you so much, everyone. That is our liquid nitrogen.
All right, that is so much. I love being able to play with these things. Now, we do have to be careful because liquid nitrogen is so cold, it can actually burn you, which sounds a little odd that something that's cold can burn you. But this is something that's very useful in that if you ever have a wart on your hand or something like that and you go to the doctor, they'll actually put a little bit of liquid nitrogen on just that spot. And it will cause a little bit of a blister, which you want at that point because then you lose the wart there. So we can use it medically. We're also playing with this outside. You do have to be careful there. All right, so next demo we're going to do for you is something called the grain elevator. And we're going to see how this works. This demo works best when there's not a lot of wind. So today, outside demos, that's what we're going to try. All right, so what we have here is something called lycopodium powder. It's this white, not white, that's not white, Dr. Mulford, that's yellow. You may all recognize this. This looks a little bit like Atlanta in the spring, like pine tree pollen. In fact, that's exactly what it is. We actually paid somebody to go out and collect pine tree pollen, and we're going to look at it here. So we're putting a little bit on the dish here, because what we want to do is we want to look at a combustion reaction. Combustion means burning, which means combining with oxygen. Okay? So we're going to try with our magic fire stick here to see if we can burn this material. All right, and no, nothing's happening. The problem is there's a little tiny bit of oxygen that is on top of the powder. And so a little small bit can burn, but not very much. So what we're going to try to do now is we're going to try to mix together our oxygen with our lycopodium, even more. All right? And then we're going to pass this across a blowtorch. Now we're going to do this by putting it in a funnel. And the funnel, when she blows out of the funnel, it's going to spread that lycopodium out so it can interact with the oxygen better. Okay? Are you ready? All right, we are ready. If we can get a honking countdown of 3, 2, 1, go! Ah, fire! Okay? All right. You want to do it again? Oh, we want to do that again. We want another fireball. So one of the things that's important about this is that any material, if it's finely divided enough, actually becomes flammable. And so we have to be careful with this. There have been some accidents industrially. It's called the grain elevator because in the Midwest, every once in a while, someone's welding on a grain elevator and this fire occurs. There was a sugar plant in in Augusta, Georgia a few years ago that actually exploded because of this. We have to be careful. All right, oh, we got some good wind here. We're going to try it again. All right, let's try it one more time. Let's 3, 2, 1. All right. Okay, that is like a podium powder. Okay. It smells like Halloween now because I usually do that in a pumpkin and get a fireball. All right, so next, we're going to work with some polymers now. All right, so we're gonna do a little bit of chemistry now. This is actually one that you can do at home because all of the chemicals for this are safe and they are ones that you can actually purchase yourself.
All right, so what we have right here in these red and blue solutions is called sodium alginate. So sodium alginate is a polysaccharide polymer that's found in the cell walls of algae. You know, that like green stuff that grows like in water. It kind of smells funky. All right, so a polymer is a compound with molecules bonded together in long repeating chains. So if you think of a bunch of people holding hands, that is what your polymer is, and each person is the molecule. So each person like holding hands is what makes up kind of what your polymer is. So in this case, our polymer is a bunch of sugar molecules linked together in a long chain. So what we have is our sodium alginate in here, and sodium has a charge of +1. So on our sugar molecule, we have sodium that will attach just on one side of the sugar molecule. So say this microphone is the sodium and my arm is this polymer. It'll attach like this along, just on one side. So whenever we put our sodium alginate into the calcium chloride, the sodium gets swapped for calcium, which has a +2 charge. So calcium has +2. This allows the calcium to be associated with 2 chains and therefore cross-link our polymers. So you'll see as we syringe some of our sodium alginate, you have to pull pretty hard because it's a tough syringe, and put it into our calcium chloride. We are going to make something that resembles gummy worms. I got you.
Do you want me to hold it?
Sure.
All right, so we're just syringing some of this fluid up here. We could have some expertise.
Oh my goodness.
Oh.
That's okay. That's why they sent you to PhD school.
All right, so it's useful to take the tip off of the syringe beforehand.
Science!
That's a lovely sound.
Thank you, thank you. We're here for the sounds.
All right.
All right, we're pouring the sodium alginate into the solution.
All right, so there's some blue. And as you can see, I can stick my hand in. It feels very gushy and gooey. All right. Thank you.
All All right, thank you very much. Now, you may have heard of that demo because the liquid you put it in, you can actually dissolve it in different things, including like lemon juice or soy sauce, and it's used in molecular gastronomy when you gotta get these little fancy like little balls of flavor that you can have. But bringing back the torch, we got another demo for you, another one looking at sugar. So, Carla, I'm gonna hand this over to you.
Hello, hello. So we're about to do an experiment called the Screaming Gummy Bear. So for this one, we've got two different things. We've got potassium chlorate and a gummy bear. We all love gummy bears, right? They're super sweet, give us a lot of energy. So with our potassium chlorate, each of these two things are going to give us two separate substances that we need for our reaction. We've got oxygen. We breathe this in, you take a deep breath in, you've got some oxygen. And then you've got sugar. This is called glucose. We need this. This gives us energy, helps us move around. And right now, she's about to heat up the potassium chlorate. It's going to break it down. Potassium chlorate has three different elements: potassium, chloride, and oxygen. Potassium, you can find it in bananas. Chloride, you can find it in salt. And then oxygen, like I said, you breathe that in. She's melting it, and it's going to break down. It's going to make it nice and gooey for our gummy bear. Our gummy bear is going to break down once we drop it in there, and it's going to cause a reaction called a combustion reaction. That means there's going to be a big explosion, so I hope you guys are paying attention for that. This reaction is a mixture of oxygen and glucose, like I said, and it's actually called cellular respiration. It's what happens when you guys breathe in your air and you're eating, and it's what gives you your energy. We're going to wait a little bit for this to melt for our gummy bear. And if you guys can't see, it's a little bit purple, which is because that's the color spectrum of potassium. It's boiling, it's melting, it's turning all gooey and liquidy. I'm waiting on it to melt. You guys like gummy bears? I really like gummy bears. I'm excited about what's about to happen to this gummy bear, guys. You ready? You're watching. You got a gummy bear right here. We're about to drop it in. 1, 2, 3. Screaming gummy bear. And all of that is happening inside your body right now. That's the screaming gummy bear.
There's an amazing amount of energy inside those gummy bears, which is why I absolutely love them. All right, we've got another demonstration for you. We're going to go to a slightly different animal. Instead of a bear, we're going to talk about an elephant. Okay?
Elephant toothpaste.
I heard somebody say elephant's toothpaste, and you're right! Okay, random fact for the day, though. If you need to clean an elephant and give it a bath, most often they use Murphy's oil soap. Who figured? But that's what Atlanta uses. All right. So right now they're adding into that some hydrogen peroxide. Now many of you may have used hydrogen peroxide before. You can buy it at the drugstore. It's used for cleaning wounds and things like that. All right. Now instead of the hydrogen peroxide you can buy, that's 3%. All right. So that means there's 3% of hydrogen peroxide and the rest is water. Now you can actually also buy 10%. It's really strong. That's what's used for bleaching hair. All right, and that's the most that you as a consumer can get. Boring. We get 30% hydrogen peroxide. All right, so that's what we've put in here. Now hydrogen peroxide will break down on its own to form oxygen gas and water, which is actually why it is stored in a brown bottle, because light makes that reaction go faster. So what we're going to do, though, it makes it go faster, but it still takes like several months, and that's just boring. So we want to try to speed the reaction up a little bit. So we're going to add something called a catalyst. A catalyst is a chemical compound that increases the speed of a reaction. Now this one is just a salt. It's potassium chloride. Now, if you think about potassium, that's just one right below sodium on the periodic table, so it's really close. But we're going to add it and see if we can make this reaction go a little bit faster here. So let's go ahead and do it. Let's put it in and see about, whoa, science! Ah, oh, whoops, wind. Okay? Oh my goodness, there's foam I love that demo. All right, so, oh my goodness. Well, our elephants are going to have very clean tusks today. So is the parking lot, but that's okay. Okay, so we did speed it up. Now, if you search on the internet, you can find, this is a favorite demo to do. And there are some people who, part of why I love the internet is there's always someone who's crazier than me who will do something that I just don't think is safe. But they have done this with thousands of liters at times. Mark Robler has the world record right now. He actually did it in a container so large that had so much force, the thing weighed a ton and he still launched it into the air because there was so much foam, which is a little bit of a problem. Oh my goodness. Now, if anybody has taken biology, maybe for some of you it was last week, some of you it might be a little longer ago, there's something we do in biology a lot of times called the iodine starch test. And so we put in a little bit of iodine to see if a sample has any starch. Our paper towels have starch in them, which is why they're turning black. Yeah, we can. It'll be okay. We'll hose off. All right. So while they finish cleaning up, oh, the next demo's me. Okay. All right. So I want to talk a little bit about gases. And gases, all right, so we have a solid, we have a liquid, we have a gas, we also have plasma. But right now, if you're talking, or I'm talking, I have a muscle in my throat called a larynx, and it's vibrating. And as it vibrates, it collides with the air molecules that are in my throat. That causes the vibrations that then travel through the air, into the microphone, into the speakers, and then out to you. All right? And I have kind of a low voice, but it's okay. So what I'm going to do is I'm going to see what happens if I replace the air that is in my throat, in my voice box, and I'm going to change it from being regular air, and that has an average molecular weight of 28. And so that's the speed. Just the number doesn't matter that much. Let's just remember 28 is where we start. And so I'm going to try to replace the air with helium, okay? I don't know if this is going to work on this windy day, but we're going to try this. Oh, a few times I get to take my mask off. All right, so what I'm going to do is I'm going to breathe this in, and I'm going to keep talking in exactly the same way. We're going to see if we can do this.
And now when I talk, the molecules in my throat are moving faster, so when my larynx vibrates, the speed of sound actually goes up, and I sound like a munchkin. Whew, that's really kind of silly. Okay, all right. I love that part. Now, the best part about this, and being a chemist, is I get access to things that most people don't normally. So I have another balloon for you. But instead of being filled with helium, this one is filled with something called sulfur hexafluoride, or SF6. All right, so regular air was 28. Helium was 4, so it moved much slower. SF6, I don't know, what's 32 plus 6 times 20? Is like 240 or something like that. It's really big. So these molecules are actually moving slower. So when my larynx vibrates, the air is moving slower, and that's going to change the pitch again. But as you're in your car, now make a prediction to the other people in your car what you think is going to happen to my voice at this time. No, we're doing it this way. Okay. All right, same thing. I'm going to keep talking exactly like this, and we'll see what happens.
Now the molecules that I have put into my voice are much more slower, and as a result, the pitch goes down. Look, I am
Okay, 3 demos that we don't let students do. And part of the reason for that is because the sulfur hexafluoride is heavier than air, it pulls in more places, like my lungs. And so there is a chance that I'm going to pass out. Luckily, I've never done that. But we'll see. Okay, now we have one more demo here. Well, we got a couple more demos for you here. Okay, so now this is one that, well, you know, we should be getting our stimulus checks here, but it still feels like all the time we're burning money, and especially for my assistants here who are in college and paying tuition. So what we're going to do now is we're going to do a demonstration for you that looks at an alcohol. And so Landy right now is adding 70% isopropyl alcohol. So that is rubbing alcohol like you get from the drugstore. And it is 70% alcohol and 30% water. And so what we're going to do, because it's what we tend to do as chemists sometimes, is she's filled this dish. It's Pyrex glass, so it's special glass. And we're going to, well, we're going to light it on fire. Now, it's going to be a little hard to see the flame today, but is it lit? Oh, careful with your hand. All right, you know what? When all else fails. All right, did we get it going? Oh, it's going. All right, now, ethanol actually burns very cleanly, and isopropyl alcohol does as well, so it's a little hard to see this, but we do have a flame. You might be able to see there's some flame you can see over here, and what we're going to do is we're going to take a $1 bill and go to the grocery store, because everything's more expensive now. But we're going to see what happens here. So Landy's going to take that. She has some special gloves on, because safety is very important. These gloves actually can go up to 1,500 degrees Celsius and keep her safe. Go ahead. So let's see what happens. She's going to put the $1, not with your finger, please, in there. Get it all the way in there. All right, so we've got our $1 in the alcohol, and now she's about to pick it up. We're going to see what happens here. All right, okay. Well, the $1 is on fire. It is burning, but now I think, oh, it's out. All right, so it burned for a while. All right, why don't we put it back in just for fun since we got the fire? We can actually go back and forth on this. Now, what's happening here? It is burning, but the alcohol has 30% water, and water takes a lot of energy to heat up. And so that water actually absorbs the energy instead of the $1 bill. Well, the bottom absorbed a little bit, but it keeps the $1 bill from burning. If you use pure alcohol, my $1 would be gone. But because the water has such a high heat capacity, ability to absorb heat, it actually absorbs the energy and we don't get the $1 to go. Okay? And so let's go ahead and extinguish that. All right, so we're going to let that sit for a minute. All right, so you can burn that paper. Let it go. All right, so we have 2 more demos for you today. Can I get one person to help me? We're just going to pull the table back. All right, so our last 2 demos for you today are 2 of our absolute favorites. And the first one, well, some of you may have seen this one before. If you watch the Mythbusters, you may have seen it as well. This is called thermite. Now, thermite is what's called a redox reaction, an oxidation reduction reaction, where electrons are moving from one compound to the other. So what we've done is we've mixed together some iron oxide, Fe2O3. It's rust. That's really all it is rust. And we're about to get started, but safety's important, so we're going to get safety glasses. Okay, so we're going to take some rust, and we've mixed it together with aluminum powder, and it's in this bottle right here. And one of the things about aluminum, or about this material, is we just had rust and a little bit of aluminum. But as soon as we mixed those together, they made thermite. Now, thermite is very stable. You could see them mixing it. It was no problem. However, it is also now considered a Class 1 incendiary device, and it's illegal to take it across state lines. So this is one we have to be very careful with, we have to be trained for. This reaction has been around for a long time. They actually use this on the railroads to help weld the ties. Okay, so into this though, we need to get it started because it's hard to get going. So they're putting a little bit of magnesium ribbon in there. Now magnesium is a metal that burns relatively easily, not super easy, but what you're going to see is, actually don't start quite yet, is we're going to start the magnesium burning. it's going to give off a very bright white light. That light you may have seen before, because that's where fireworks get their light from. That's then going to start the thermite reaction. Now I'm going to tell you what you're going to see, just so you have kind of an idea what to look for. We're going to go from room temperature to 3,000 degrees Celsius in less than 1 second. And when this reaction goes, it gives off an incredible amount of energy. We're going to see some sparks coming up, so my demonstrators are going to step back. But then, that is hot enough that it can melt the iron that was part of the rust. So if you watch the bottom of the pot, you will actually see molten iron come pouring out the bottom that we have produced by a chemical reaction. All right, so let's go ahead and start this. All right, we see that bright white light like a firework. All right, it's going to take a minute. We had a long chain. Oh, it went out. Let's try one more time. Go ahead. Go ahead and light it a little lower down. There you go. Oh, there you go. All right. All right, so it's going to go down into the thermite. It's going to start this reaction, hopefully. Oh, there we go. We've got the reaction going. Watch the bottom of the pot in right about there. It is. There is the molten iron pouring out of the bottom of the pot. So if you put that in front of a railroad tie or above it, right, you can do a little welding. And do we have our sample? Yep. I love that demo. It's nice and warm. I can warm myself. It is actually probably still about 2,500 degrees. When it cools down, it will create a lump of iron that's in there. Makes a great paperweight. A little bit of sand got stuck in there because we caught it in the sand. We did that, okay? So that's the thermite reaction. That was a lot of fun. And we have one last one for you here that's a favorite of mine. So if you have the thermal glove, we can just drag it back out of the way. All right, so we're going to bring forward our materials we need for our last one. We're going back to liquid nitrogen because, come on, it's liquid nitrogen. It's fun stuff if you are safe with it. I have spent some time with these students over the last couple of weeks, training them, making sure they understand the science behind all of these demonstrations and the safety. Okay, so now this demonstration, we're going to look at the interaction between liquid nitrogen and water. And so rolling out here in BB-8, our own BB-8 here, is a very large container of liquid nitrogen. Whoa, sorry about the feedback there, folks. So this contains about 60 liters. We only want about 10 liters. So we're going to pour that in. All right, it's a team effort because it's heavy. It only has a density of 0.89 grams per milliliter, but it's also a lot of it. You guys got it? You need help. All right, I'm going to watch and see how much. A little more, a little more. You're seeing a little bit of a cloud forming right now because it's actually causing a little more. Just tip it a little bit more. How are we doing in here? That's probably good. Okay, so the cloud you're seeing right now, because the nitrogen is cooling down water droplets in the air, moisture in the air, and forming liquid water. A cloud is actually liquid water droplets. So what we're going to do now let's talk about nitrogen for a second. Right, that was 77 Kelvin, 300 degrees below 0 Fahrenheit. We're going to add to that boiling hot water, 200 degrees Fahrenheit. So we are going to have a 500 degree temperature change here. And we're going to see what happens when we do that. Okay, just about ready. All right, we're getting the gloves on. Because it's boiling water, we're using hot mitts. Whoa, they're Walmart's best hot mitts. All right, so let's go ahead and grab your minion, because every good scientist needs a minion. So we got our minion bucket here. Got it. Okay, we're going to do one more of these countdowns. Get yourself nice and close. And all right, let's get a 3, 2, 1, go. All right, we've got a cloud coming out here. Whoa! Oh. And this will go for a little while as we boil off the rest of our nitrogen. All right. Thank you all so much. That's actually our last demo of the morning. I'd love to keep doing this to you, for you, for hours. Not to you, for you. But if we could just take a moment and thank all of our demonstrators here with a little bit around the honking here. So thank you so much.